or visible? Is it moving? So this is the problem on power stages in induction motor. The problem is going like this. A 3-phase 4-pole 50 Hz star connected induction motor on full load develops a usual torque of 300 Newton meter. The rotor EMF is completing 120 cycles. If torque loss in friction is 50 Newton meter, calculate slip net output power, rotor copper loss per phase, rotor efficiency, rotor resistance per phase if the rotor current is 60 ampere in running condition. Shall we proceed to see the solution? So first you write the given data. So P is equal to 4, F is equal to 50 Hz, which is star connected, and useful torque of 300 Newton meter. Useful torque means it is the shaft torque that is only useful to us, or it is the final output torque. You have to note down that. So this useful torque is nothing but it is T out or T shaft. That is the final output torque. That is 300 Newton meter. The rotor EMF is completing 120 cycles per minute, and the torque loss in friction. So this is the loss torque, because the torque will be developed in the rotor, and some of the torque will go as base due to friction, and after that only we will get the useful torque. So this is the T loss, that is equal to 50 Newton meter. So this is the given data, or these are all the given data. So first we need to calculate the slip. You see here, so this is the given data I have written. E is equal to 4. Everything I have written here. Now we need to calculate the slip. Slip is nothing but ns minus nr by s. That is the value of slip. But here we do not know the rotor speed. Rotor speed, it is not given here. But ns, it is available from the formula. So ns is equal to 120 f by p. So frequency they have given as 50 Hz. So that is the stator frequency divided by 4. So it comes around 1500 RPM. So this is ns. So ns we know. But nr, it is not given in the problem. We cannot compute also nr from the given data. So then how to compute the value of slip? So you have to use this relationship for this, because the rotor frequency they have given. The rotor frequency is 120 cycles per minute, and we know the equation that rotor frequency is equal to slip times stator frequency. So from this formula I can write slip is equal to rotor frequency by stator frequency. So here rotor frequency they have given 120 cycles per minute. In order to convert this 120 cycles per minute in terms of hertz, you have to divide 120 by 60. So if you divide 120 by 60, you will get 2 hertz. So 120 cycles per minute, it is equivalent to 2 hertz. Okay. So here you have to substitute 2, and the stator frequency already it is given as 50. So 2 by 50 is equal to 0.04. So this is nothing but 0.04, or in terms of percentage it is 4%. So that is the value of this. Any doubt in this? Okay. If it is clear, we will proceed to the next. Next, we need to compute the net output power. Next, we need to compute the net output power. Net output power is nothing but that is the P out. That is the P out. This is the P out. Okay. Or this is the power available in the shaft. Okay. So, what is the power available from the induction motor? It is 2 pi nt by 60. So, P out, I can write 2 pi nt by 60, whereas N is NR and T is nothing but that is the T out, or shaft torque, or useful torque. Okay. So, here TSH is already given as 300. That is the final output torque or torque available in the shaft, or it is the useful torque. And similarly, P output is nothing but that is the final output or net output, P output or P shaft. In any way you can write this. This is P shaft or P final. Anyway you can write this. So it is 2 pi NR TSH by 60. So here we know the value of TSH, that is 300, and rotor speed we do not know, that we need to compute. So the rotor speed can be computed using this formula. So NR is equal to 1 minus S into NS. Okay. Yes, already we have computed, that is 0.04. So 1 minus 0.04, synchronous speed, it is already computed, multiplied by 1500. This is equal to 1440 RPM. So you substitute everything here, you will get the final output, the useful output or P output or power available in the shaft. It is coming around 45.216 kilowatts. Okay, 45.216 kilowatts. So this we have computed now. This is over. Then next what they are asking, rotor copper loss per phase. So in order to compute rotor copper loss, we need to use this relationship. P copper loss is nothing but S into P2. This relationship we have already derived from power flow equation of induction motor. So S into P2 is nothing but 2 pi NST by 60. P2 is the input to the rotor. So after putting all the values, 2 pi, ns is 1500, T is 350 divided by 60. So you will get 0.733 kilowatts per phase. It is 2.199 kilowatts. That is the total rotor copper loss. They are asking us to compute rotor copper loss per phase. So you have to divide this value by 3. So copper loss divided by 3, that is for per phase, that is equal to 0.733 kilowatts per phase. So that is the copper loss per phase. So we have computed the net output power and we have computed copper per phase. Till now, anybody is having any doubt? If anybody is not understanding, you can ask me. Shall I proceed further? Yes. Some people are joining very late to the class. Now next we need to find the rotor efficiency. Rotor efficiency is nothing but rotor output divided by rotor input. So what is the rotor output? That is the mechanical power output, Pm. And what is the rotor input? That is P2. So the rotor efficiency is nothing but Pm by P2. P2 already we know, that is 2 by nsp by 60. But Pm we do not know. You have to look at the power flow. What is our power flow? For clarity, you can draw this. This is rotor. This is P2. This is copper loss. This is Pm. So the rotor efficiency is nothing but rotor output, that is Pm, divided by rotor input P2. Pm is nothing but 2 pi nRT by 60. That is my Pm. Okay. And P2 is 2 pi nsp by 60. Right. So now we need to find this T. Of course, here also no, we should need to find this T that nobody asked me. This T. This T is not 300 Newton meter. Okay. 300 Newton meter, it is the final torque available in the shaft. Okay. That is the final torque available in the shaft. That is TSH. If you add the torque lost due to friction to this THS, then only you will get this total torque which is available in the rotor. The torque available in the rotor is T. If you subtract the torque available in the rotor is T. If you subtract torque loss due to friction from the total torque or torque available in the rotor, you will get shaft torque or T out. Here shaft torque is given as 300 Newton meter. Torque loss due to friction is given as 50 Newton meter. So if you add these two, you will get this is the torque actually produced in the rotor. But that is not available in the shaft because of the mechanical loss. Due to mechanical loss only, some of the torque is going as this. So the torque available in the rotor is nothing but shaft torque plus torque lost due to friction. So the T is 350 Newton meter. Right? And same way here, you can substitute torque as 350 Newton meter. This is 350 Newton meter. This is also 350 Newton meter. That is torque available in the rotor. After here only the torque is going as waste. This is T loss. Then only you are getting the final output torque or shaft torque. Some of the loss is going as waste. Some of the torque is going as waste. So if you divide these two, 2 pi ns T by 60 divided by 2 pi ns T by 60. If you divide these two, this is the rotor efficiency, 96%. Is that clear or any doubt you have? The torque, have you understood? The torque available in the rotor is T, and the useful torque is T out or TSH. And the torque is going as waste due to mechanical loss is nothing but T loss. Is this point is clear? Yes. Now next we have to find the rotor resistance per phase. They are asking us to find the rotor resistance per phase, and they have given the rotor current as 60 ampere. Now, how to find the rotor resistance? So we know rotor copper loss per phase is nothing but I squared R, or I squared 2R, that is rotor current square, into rotor resistance. So rotor copper loss per phase we already know, that is 0.733 kilowatts we have computed. And the rotor current is 60 ampere. So if you divide 0.733 kilowatts with respect to 60 square, you will get rotor resistance. That is rotor resistance per phase. So 0.2036 ohm per phase. Is it clear? Any doubt you have, you can ask me. You can stop and you can ask me. Anything if you are not clear, you can ask me, because I do not know. I am teaching, I am going. I do not know whether you are understanding or not. If you say yes, I will proceed. Otherwise, if any doubt you have, if anybody is asking, I am ready to clarify it. So this is the solution for that problem. Shall we proceed next? Yes. So next topic in your syllabus is equivalent circuit of induction motor. Okay. So I told you that equivalent circuit is nothing but it is the mathematical model of any machine. Already we have seen the equivalent circuit of transformer, equivalent circuit of DC machine. So now we need to see the equivalent circuit of three-phase induction motor. Generally, if we model the three-phase induction motor, the model is for per phase only. If we give mathematical model for per phase, the same model is applicable for other two phases, provided all the three phases are balanced. Okay. If all the three phases are balanced, then whatever the mathematical model we are developing, it is applicable for all other phases. It is like a transformer. Equivalent circuit for single phase transformer we develop. So that is applicable for three phase transformer also. Each phase if it is balanced. Right. And here, in order to develop equivalent circuit for induction motor, the equivalent circuit is very much similar to the transformer because induction motor, in other words, it is called as rotating transformer. Why? Because it works on the principle of mutual induction similar to the transformer. So this is how you can develop the equivalent circuit. So the equivalent circuit is very much similar to the transformer. You have a stator in the induction motor that is very much similar to primary side of the transformer. So here I have written here. So primary side is very much similar to stator of induction motor, and stator it is having the stator resistance R1 and the stator reactance, or in other words stator leakage reactance X1, very similar to the transformer R1 X1, and you have the core resistance RC or R0, and you have the magnetizing reactance X0 or X1, very similar to the transformer, right? And coming to the secondary side or the rotor side, you have the rotor resistance R2 and you have the rotor reactance, that is S times X2, because the rotor parameters, it is getting affected by slip. So the reactance is nothing but S times X2 that we have already derived. And the rotor induced EMF is S times E2 that we have already derived. The rotor resistance, it is independent of the slip. Why? Because it is independent of the frequency. Right. So now the stator and rotor, it is coupled to the mutual. It is coupled through mutual induction. So the stator and rotor mutual induction coupling can be shown as mutually coupled circuit. So this is the stator winding, this is the rotor winding, both are mutually coupled. So this is the air gap. Okay. Two lines indicate the ferromagnetic core. So R1 X1, R0 X0, and here SX2, SE2, R2. So this equivalent circuit, it is for per phase only. The same thing it is applicable for other phases if all the three phases are balanced. So now here we are doing one small modification in the equivalent circuit. Now the rotor current can be written as SE2 by root of R2 squared plus SX2 the whole square. So this is the rotor current. So this is my rotor current. This is my rotor current. This is written as SE2 voltage divided by impedance, root of R2 squared plus SX2 the whole square. That is what here it is written. And if you take slip outside, it gets cancelled and the same equation is coming like this: E2 divided by root of R2 by S the whole square plus X2 the whole square. So this rotor side equivalent circuit R2 SX2 E2R, that is SE2, okay, can be written as, because this is very much similar to SE2 divided by R2 squared plus SX2 the whole square. It is very much similar to E2 divided by root of R2 by S the whole square plus X2 square. If you write like this or if you write like this, that will circulate the same current. This is going to circulate the same magnitude of the rotor current. So the equivalent circuit can be redrawn like this: E2R becomes E2, X2 it is becoming X2, and R2 it is becoming R2 by S. Right? So if you have this equivalent circuit or this equivalent circuit, it is going to circulate the same rotor current. Now again some modification has been done to the circuit. rotor side, this R2 by S can be written as R2 plus R2 by S minus R2. Just I am adding R2, I am subtracting R2. And if you are grouping it properly, R2 plus R2 into 1 by S minus 1, I can write like this. This can be grouped like this. R2 plus R2 1 by S minus 1. And finally, this R2 by S, R2 by S can be written as R2 plus R2 into 1 minus S by S. So the same equivalent circuit, this R2 by S can be split into two components. One is R2, another one is R2 1 minus S by S, and this is called as load resistance. R2 into 1 minus S by S, it is called as load resistance. This load resistance is the electrical equivalent of the mechanical load. Okay. So to the induction motor, the mechanical load is generally coupled to the rotor. And that mechanical load, how it can be modeled? It can be modeled as the load resistance. So this load resistance is nothing but it is the equivalent resistance representing the mechanical load. Right? It is the equivalent resistance representing the mechanical load. So when the load is changing, correspondingly speed will change, rotor speed will change. Accordingly, the slip of the rotor also will change. The change in the slip because of the change in the load, that is reflected in the load resistance RL. Till now, is this clear or any doubt is anybody having? So the mechanical load, it is equivalently represented using the resistance. So when you change the load, that is reflecting the speed, that is reflecting the slip, and that is represented as the equivalent resistance. So now, after doing this modification, so finally you can have the equivalent circuit like this. So you have R1, X1, R0, X0, E2, R2, X2, and this is the load resistance that is varying with respect to load. So this is very much equivalent to the mechanical load. Okay. So this is the equivalent circuit of induction motor. And similar to transformer, you can either transfer all the secondary side parameters to the primary or all the primary side parameters to the secondary. In the case of induction motor, you can transfer all the rotor parameters to the stator, or you can transfer all the stator parameters to the rotor. Okay. But in the case of induction motor, it is preferred to transfer all the rotor parameters to the stator because rotor is rotating, stator is stationary. So it is very much amicable if you transfer all the secondary side parameters or all the rotor side parameters to the stator. So if you transfer all the rotor side parameters to the stator, your X2 becomes X2 dash, R2 becomes R2 dash, RL becomes RL dash, IL becomes I2 dash, and E2 becomes E2 dash. And X2 dash, R2 dash, RL dash, I2R dash, E2R dash, everything, no, the value, it is very much similar to the transformer. You can refer transformer referring secondary side parameter to the primary. Similar analysis only here we are doing, referring rotor side parameter to the stator. Okay. And we know very well that we are shifting that shunt branch to the front end for easier analysis. So this is moved to the front. So it is moved to this front. So R0, X0 is moving front. Now R1, X1, X2 dash, R2 dash. So now this R1 can be added with R2 dash, that is R1E. R1E is nothing but R1 plus R2 dash. X1E is nothing but X1 plus X2 dash. Okay. And finally, the equivalent circuit referring to the stator side, it is coming very simple like this. This is very much similar to the transformer equivalent circuit referring to the primary side. Okay, it is very similar. X2 dash is X2 by K square, R2 dash is R2 by K square. So whatever analysis we have done in transformer transferring secondary side to the primary side, here it is very similar. Secondary side parameter to the primary side or rotor side parameter to the stator side. Right? Till now, any doubt is there? So if you want, you can write like this. R2 dash is R2 by K square. You want, you can write. R2 dash is nothing but R2 by K square. X2 dash is nothing but X2 by K square. I2R dash is nothing but K into I2R, and E2R dash is nothing but K into E2R. It is very similar to the transformer referring from secondary side to the primary side. That you can also refer in the book. Okay. Now, next topic is power equation from the equivalent circuit. Right. This equation is very important to solve problems in gate examination. So from the equivalent circuit, what is the power output from the rotor? So again, you have to take the power flow of induction motor. You have the rotor here. This is the rotor, and P2 is the rotor input, and PM, that is the rotor output, or that is the power equation from the equivalent circuit. You can derive PM in terms of equivalent circuit parameters. Sometimes this is very much useful to solve problems in gate examination. The derivation is very simple. What is PM? PM is P2 minus P copper loss. Okay. And P2 is nothing but P copper loss divided by S. Or in other words, P copper loss is nothing but S times P2. So from this I can write P2 is nothing but P copper loss by S. So this I have written. What is my P copper loss? P copper loss is nothing but 3I squared R2. So from the equivalent circuit I am deriving. This is the equivalent circuit I am referring to the stator side. So I2R, it is not simply I2R, it is I2R dash. And R2 is nothing but it is R2 dash. So 3I2R dash the whole square, R2 dash. Simply you substitute these two in this equation. So PM is nothing but P2, that is P copper loss by S, and minus P copper loss. So you see here, this is P2, that is P copper loss by S minus P copper loss. So if you simplify, you will get 3I squared R2 into 1 minus S by S. So this is the power output from the rotor in terms of equivalent circuit parameter. Equivalent circuit parameter is nothing but rotor resistance, rotor current, and slip. And from this, we can get the torque developed also. Torque developed is nothing but PM is nothing but omega R into T. So from here, T I can write it as PM divided by omega R. So what is Pm? Pm already we have 3I dash 2R the whole square R2 dash 1 minus S by S. And this omega R I can write in terms of revolution per minute 2 pi NR by 60. And you substitute this NR as Ns into 1 minus S. You substitute this NR as Ns into 1 minus S. So this is the torque and power equation in terms of equivalent circuit parameters. Any doubt in this? Omega R is radians per second, NR is revolution per minute. So 2 omega R I can write it as 2 pi NR by 60, and rotor speed I can write in terms of synchronous speed, that is Ns into 1 minus S. Any doubt in this? If you are having any doubt, you can ask me. Shall I proceed? Yes. You take down this problem. This is the homework problem. I am not going to solve this problem in the class. You solve it by yourself. If you have any doubt, you can ask me. A 440 volt 3-phase 8-pole 50 hertz. The 40 kilowatts, you don't take that one. That is wrong parameter. That is why I have crossed it. A 440 volt 3-phase 8-pole 50 hertz star connected induction motor has the following parameters. R1 is 0.1 ohm, X1 is 0.4 ohm, R2 dash is equal to 0.15 ohm, X2 dash is equal to 0.44 ohm. This is the problem on equivalent circuit referring to the stator circuit. That is why they have given R2 dash and X2 dash. Stator core loss is 1250 watts. Mechanical loss they have given as 1000 watts. It draws a no load current of 20 ampere at a power factor of 0.09 lagging. This is very much similar to transformer. Here also you have no load current. Every machine will have no load current to meet the core loss and mechanical loss. While running at a speed of 7 to 7.5 RPM, that is the rotor speed. You need to calculate input line current, torque developed, output power, that is Pm. Okay. You calculate Pm, so that notation I have mentioned Pm, because simply if I give output power means you will be having confusion that whether it is final output or rotor output. It is a rotor output, Pm. Torque developed is T. So that is the torque developed inside the rotor. It is not final torque. It is not a shaft torque. It is not a useful torque. It is the torque developed in the rotor. Then efficiency of the machine they are asking. Complete. The complete efficiency of the machine they are asking. And of course, they are asking us to use approximate equivalent circuit. So this is the approximate equivalent circuit. So this equivalent circuit you can use. This is the approximate equivalent circuit. So till now, any doubt anybody is having? Only one topic is left out in unit 1, that is test on induction motor, and one problem we need to solve in this test on induction motor. So maybe in another 2 classes I will complete the unit 1. Whatever I am teaching, is that clear to you all people? Okay, shall we leave the class? If anything you want to ask me, you can ask